What do you think is the relationship between heat, a network, and a zombie? That is exactly the question we have been working on. I'm Zahra, and today I have with me Leo, Malaika, and Katie. And this summer, we have been researching on a very special type of network known as small world. It can be seen all around us in the neural network of worms and social networks like Facebook. We use tools from linear algebra to study the characteristics of small worlds and see how they differ from other networks. Our main goals for this research was one, to understand the even and odd Laplacian, their properties and how they differ from each other. Two, see how heat diffuses in small worlds and use the odd and even Laplacian to solve the graph heat equation. Three, understand and define small world networks and their dynamics. And finally, understand epidemiology on small world networks using the SIR, SIS, and the zombie models.
Well, we can study the properties of small graphs simply by looking at it. This strategy doesn't really work for large networks. A common solution to this problem is to study graphs using linear algebra. Graph Laplacian provides a very efficient way of studying graphs with matrices. One of the most commonly used Laplacian, also known as the even Laplacian, is formed by multiplying the incidence matrix to its transpose. The product is going to be a square matrix of v times v, where v denotes the order of the graph. The matrix contains important information about the graph, especially concerning its vertices, as we will see later. Interestingly, if we just reverse the order of the multiplication, we'll get another matrix, usually called the odd Laplacian. This is going to be a very similar matrix, but with size e times e, which is the number of edges in the graph. During our summer research, we compared the two Laplacians to see the similar and different properties they exhibit. Here is an example of a graph and their even and odd Laplacian respectively. So here are some of the properties of the even Laplacian. First, for each entry ij, the entry is going to be vi dot product vj. Next, the diagonal represents the degree of each vertex. So for each entry that is not on the diagonal, the entry is going to be 1 if the vertex I and j are adjacent. It's going to be 0 otherwise. One way to look at this is that the even Laplacian can be seen as a diagonal matrix of no degrees minus the adjacency matrix on vertex. Next, when multiplying to an initial state x of a heat equation, each entry will represent the sum of difference of the current entry to its neighbor. This is why the matrix is called the graph Laplacian, corresponding with the Laplacian operator in differential equations. Finally, the dimension of the kernel is going to be the same as the zeroth Betti number, which is the number of connected components. The implication of this is that a heat equation on the graph is stable if and only if each connected components have the same initial value. The odd Laplacian exhibits very similar properties, but are more edge-oriented. For instance, non-diagonal entries represent the adjacency of edges instead of vertices. Notably, here the entries can take value -1 as well as 1. The sign depends on how the edges are connected. When the direction flows the same way, negative is -1, otherwise it's going to be +1. Finally, there's an interesting correspondence between the dimension of kernel and the first Betti number. One problem we have yet to solve is what is a graph-theoretic interpretation of a heat equation on odd Laplacian.
A lot of our research is focused on a certain type of graph, small world networks. The Watts-Strogatz generative model characterizes these graphs with two key features. First, all small world networks have small characteristic path lengths. This means that the distance between pairs of vertices should be relatively small, and the average shortest path length should also be small. The presence of shortcut connections between some vertices within a small world network results in this feature. Additionally, small world networks should have large clustering coefficient. This coefficient measures the extent to which vertices linked to any given vertex V are also linked to each other. It essentially asks, am I friends with my friend's friends? Anyways, small world networks have high coefficients because each vertex of these graphs is linked to a well-connected set of neighboring vertices. A network is considered to be very clustered if its coefficient is higher than that of a random graph with the same number of nodes and the same average degree. You may be surprised how common these types of networks are. Some examples include food webs, social media networks such as Facebook, and the neural network of the roundworm, which is commonly used in biological research. Now, to identify what actually is a small world network, researchers use two indices. Sigma was the original indice and compares the graph of interest to a randomized version of itself via both the clustering coefficient and the characteristic path length of both graphs. These randomized graphs are formed through the classic Erdos-Rényi model, where each possible pair of links in the graph has a possibility p of generating an edge to each of the other nodes. Sigma values range from 0 to 1. Graphs displaying the most small world properties correlate to intermediate values. However, sigma does not scale towards larger graphs, making it harder to work with when using certain data sets. Therefore, we chose to focus our research on omega, which is the newer of the two indices. Omega compares the graph of interest to a lattified version of the graph. Similar to sigma, the comparison is drawn through clustering coefficients and characteristic path lengths. Omega values can range from -1 to 1, with intermediate values again being characterized as small world networks. The omega index is able to more accurately identify these types of networks as compared to sigma, and also allows for greater scaling, which proved quite helpful when we wanted to study larger networks such as disease modeling. You might be wondering how these types of graphs are actually generated. Well, in addition to defining these types of networks, the previously mentioned Watt-Strogatz model is also used to create these small world graphs. The model begins with a regular lattice graph, which is seen here on the right. All the nodes have the same degree, and these kinds of graphs have a high clustering coefficient. However, they lack small characteristic path lengths. They have none of these so-called shortcuts. The Watt-Strogatz model accounts for this disparity through a process of rewiring of these lattice graphs. This involves adding some of these shortcuts, which connects distant sections of the graph, as shown here on the left. This process maintains high clustering but introduces shorter characteristic path lengths. The resulting graph is a small world network which can model many real-world phenomena such as heat diffusion.
Imagine that you have hot tea in a cup. What would happen if you left that cup alone for 30 minutes? It would cool, right? This happens because of the diffusion of heat in a system. Continuously, it can be modeled using the heat equation. This equation states that the rate of change of temperature is directly proportional to the second partial derivative of the change in temperature with respect to position. It can also be expressed linearly using the Laplacian as shown. We found the solution to the graph heat equation, and it can be used to find the temperature of a graph at any given time. It states that the temperature of at a time t is equal to e to the power of -k delta t multiplied by the initial state v0, where k is a real number and delta is the graph Laplacian. This led us to investigate how the temperature of a network changes with time. To understand this, we must first define convergence time. In this case, it was the time it took for a system to reach a steady state, where the temperature is no longer changing. To find this, we tried two things. First, we found the time it would take for all the nodes in the network to reach average temperature. However, this was inconclusive for non-connected graphs. The next thing we tried was using the heat equation to calculate the node with the highest temperature in the graph minus the node with the lowest temperature in the graph at any given time. This value would change until the network reached a steady state. Furthermore, this approach works for connected and non-connected graphs. On modeling the difference in temperature with respect to time, the convergence time can be seen as a point in the graph where the gradient first reaches 0. As hypothesized, different networks diffuse differently. Here, we compared 3 different networks: scale-free, random, and small world network. As can be seen from the degree histograms, these 3 graphs have very different degree distributions. Scale-free networks have few nodes acting as large hubs. In the diffusion curve, we notice a point where the gradient changes sharply. In this random graph, the average degree of connectivity is high. Here, we notice an extremely fast diffusion curve with the convergence time very close to 0. Small world networks have high clustering coefficients and low characteristic path length. The convergence time shown is slower than the other two, and the diffusion is smooth. This led us to the conclusion that the structure of a network affects its dynamics. Going back to the heat equation, one thing we notice is that the Laplacian being considered is the even Laplacian. This led us to question whether the orientation of the network, meaning the odd Laplacian, affects the diffusion of heat in the network. And as we can see from the two graphs shown, it does. In both cases, the diffusion took the same shape for both the even and odd Laplacian. However, the temperature that they diffuse to is different. Experimentally though, a network will only converge to one temperature. This means that the orientation of the network affects the diffusion. Thus, we made three conclusions. Over time, the temperature of a network converges to a certain value, the structure of a graph determines its dynamics, and the orientation of a network, odd Laplacian, affects the heat equation.
The final phase of our research was concerned with modeling epidemics on small world networks, something very applicable today given the ongoing pandemic. There are three main factors that are taken into consideration when doing so. The first is the contagion, so how contagious the infectious agent is. And the second is the strategy of spread for the infectious agent. The final factor is the topology. And throughout our research, we saw that the topology of a network or a graph greatly determines how an epidemic forms and spreads in that network. For example, for a vortex to have a high degree, which means it has a lot of neighbors, it can infect more nodes per unit time because it has more neighbors than compared to a node that doesn't have that many neighbors. Similarly, having a lot of clusters or having a low characteristic path length can also speed up the transmission of a disease. For these reasons, we saw that epidemics do not usually form, or when they do form, they spread very slowly in graphs like path graphs. Whereas in a small world network, the transmission of the disease is much faster, mainly because it has a high clustering coefficient and low characteristic path length. The transmission of a disease is the fastest in a complete graph because every node is connected to every other node. We then moved on to more specific epidemiological models. So the first model we studied was the SIS model. And the continuous SIS model assumes that the disease confers no long-term or no long-lasting immunity for the infected patients. And this allows the disease to obtain a steady state. There are only two subgroups of the population here, the susceptible and the infected, and they keep interchanging within each other. So this is the susceptible equation, and this is the infected equation. The beta here stands for the infectivity of the infectious agent, and the alpha here stands for the fraction of the infected population that recover and then re-enter the susceptible group. The continuous SIR model assumes that the disease does confer long-term immunity to the recovered individual. And as the name suggests, there are three subgroups here, the susceptible, the infected, and the recovered. Again, we have three equations relating to each of these groups. The beta, again, refers to the infectivity of the infectious agent, and the gamma here refers to the recovery rate, which is usually taken to be the reciprocal of the average duration of the disease. In this slide, we see how the different models look on graphs. So in the SIR model, we can see that the infections peak and then they go down, and this is because immunity is conferred to the recovered individuals. And undoubtedly, that's a graph we've seen very often in the news lately. In contrast, the SIS model, we see the curves plateau, so they reach a steady state, and that's because immunity is not conferred. So the infected and the susceptibles keep interchanging with each other in this steady state equilibrium. We also studied the zombie model, which is a variant of the SIR model. It's based on popular zombie culture, and again, it has three subgroups: the zombie group, the susceptibles, and the removed group. The removed group contains anybody who dies of zombie-related or unrelated causes. Unlike the SIR model, the zombie model is a little more complicated, mainly because there are two mass action transmissions here. You can become a zombie if a susceptible is infected by a zombie, or the susceptible can just die due to natural causes, and then there is a probability that they will be resurrected as a zombie. For this reason, the model that we studied showed that there is no human zombie equilibrium and everybody eventually turns into a zombie in the end. We also tried to have stochastic simulations of the epidemics, which requires the simulation of Markovian processes where the nodes change status over time. And this can be done using algorithms like the Gillespie algorithm or the event-driven algorithm. And although the event-driven algorithm is a little faster than the former, they do produce the same stochastic process. Here in this figure, we can see the stochastic simulation of an epidemic on a small world network using the SIR model at T0 and T4. At T0, we introduce an infected node, and we can see how the disease evolves over time and how the nodes are infected at time T4.
In the future, we hope to find a graph theoretic interpretation for the heat equation on the odd Laplacian, investigate heat diffusion on other types of networks. Furthermore, we hope to understand the rescaling effect of a network on its small worldness and expand our research of small world networks to other disease models to incorporate global data. Thank you.